Welcome back to the second part of this video on consciousness and the collapse of the wave function. We left off in last video basically with a simple model of how we could potentially couple consciousness with the collapse of the wave function. And our conclusion in the end was we couldn't really get it to work. We had something called the Zeno problem or the Zeno effect that came into, that basically revealed itself for our simple model. And we need to now find a way around that. And that's what we're going to discuss in today's video. So to jump into this, basically, we will start talking some about integrated information theory. We're not going to go into the details of integrated information theory because I already have a video on that. So if you haven't seen that video, I would recommend watching it. You can see a link in the description. But basically what integrated information theory tells us is that it gives us a way to measure consciousness, both in terms of qualitative aspects, but also quantitative ones. So we measure the level of consciousness or the level of a phenomenal experience by means of the integrated information phi. So we can see that denoted here. We also have something called a Q-shape, which determines basically the qualitative aspect of this experience. So both of those components make up the integrated information theory. And it's pioneered by Tononi, so the guy that we have in the slide here. And what we want to do now is we want to use this framework and reconcile it with the observations that we see in quantum mechanics. It's worth maybe discussing why we're picking integrated information theory to begin with. And it's because it's one of the few models that actually gives us a quantitative account for consciousness. So in general, there are quite a few models that model consciousness in some way, but they're usually not giving testable predictions. And that's really the strength of integrated information theory and why we tend to use it in a setting like this. So equipped with that model, we now want to make it compatible with the observations we see in quantum mechanics. And this is not very simple. The first thing that you might consider doing when you try to reconcile these two is to use the measure phi as a super resistant property. So you would basically have phi and phi causes collapse. There's a problem with that, which is that many systems can have the same phi. So the same amount of integrated information, but they're not necessarily the same. So it turns out to not be the best metric for basically separating states. What we can do instead is make use of the Q-shape. So that gives you also the qualitative aspect of the phenomenology of the experience. And if you combine those two, you then get a measure that would basically separate your states in an adequate way. So we wanted to find Q-shaped collapse operators, one of each dimension of the Q-shape. So normally your Q-shape is multidimensional, and you would want it to be able to collapse into multiple of these dimensions. And so you would define several of these collapse operators for that purpose. And the eigenstates of these operators would then correspond to the states that you can fall into in a superposition collapse. So that is very much the same as the notion of quantum mechanics and how we do it in the physical realm, let's say when we're doing predictions there. So that's motivating the decision for these operators. There is a problem with this view also. So it's not as straightforward as just doing this, but the problem that we run into is that both phi and the Q-shape may depend on the mass and momentum of a certain particle. And if you're familiar with quantum mechanics, you know that due to Heisenberg's uncertainty principle, you can't measure these two properties adequately at the same time. So in other words, they don't commute, is what we call it. I have an illustration of that down to the bottom right here. And what this basically indicates is that if you determine delta x, which is the position, with a high degree of accuracy, you're basically the speed or momentum of this particle would be quite uncertain. And that's represented by the blue distribution here. So you can't specify these in very, in granular detail for low mass particles at once. And the consequence of this is that for low mass systems, so individual particles, for example, you're not going to be able to necessarily determine phi and q adequately. And so that's a big problem for this theory. There are a number of ways that you can get around this though. So one way you could do is you could define phi to be 0 for all low mass particles. So that would basically mean that they're not conscious and we don't have to deal with the collapse of the wave function in that case. So we would circumvent the problem that way. Another way that we could do it is we could redefine the phi and also the Q shape to only depend on the probability, so the PDFs of these masses and also momentums. So instead of using the actual positions or the actual values of these quantities, you could use the entire distribution itself. And then having this sort of spread out, well, shape or property would not be a problem for our models. Another way of doing it would be to extend IIT and make it more sophisticated so that it's defined also over quantum states. And that's something they're investigating in the paper. So that's something we'll also briefly talk about. In order to do this, in order to reconcile IIT with quantum mechanics, there are a number of models out there. These three are three examples they bring up in the paper, and the one they're using is the last one here. So basically, the bottom line of what they're doing is they're extending the notion of a Q-shape to also include what's called quantum Q-shapes. And yeah, this is an extension of the classical ones, where there is a mapping from the classical Q-shaped states to a subset of these quantum Q-shapes. So we call those quasi-classical Q-shapes. So there's a one-to-one correspondence between the two, but overall, the set of quantum Q-shapes is bigger to accommodate for the restrictions that we have and the extensions that we need to make. The quasi-Q-shapes, quasi-classical Q-shapes, correspond to the determinate states of consciousness. So those are, yeah, as I said, very similar to just what we have from standard IIT. And the other quantum Q-shapes would correspond to superpositions of quasi-classical Q-shapes. And this is an interesting concept that we're saying here. So we're saying that basically you have a superposition of different states of consciousness, and it's quite arbitrary what that even means. So what you get into here is a similar situation to what quantum mechanics gives us to begin with, right? We're saying in quantum mechanics that for physical systems, we have a superposition of potential states that we could be in, but we're not making a deterministic claim as to which one we're in. We're doing the same thing here with consciousness, which, to some extent is what we want to get around when we're saying that consciousness collapses the wave function. So you could say it's kind of like going backwards in a sense. But for now, this is, a way to model what we're observing or potentially observing to see how well they align. And so that's a sacrifice we're willing to make for the moment being. In addition to these quantum Q-shapes, we also have quasi-classical states of quantum systems. So quantum states that quantum IIT associates with quasi-classical Q-shapes or what these are. So, you would normally have a mapping between something physical and then also a Q-shape, because you want to solve the problem of causality. So you want basically your consciousness to be able to have a causal role in the physical world. This is one of the very central problems when we're discussing, for example, the mind-body problem. And in order to circumvent that, you would need some way of mapping Q-shapes of consciousness to actual physical realms. So that's why we have this mapping from Q-shapes to quantum states. And so every state of a quantum system can then be represented as a superposition of quasi-classical states. So we're doing exactly the same thing as we did for the Q-shapes, but now also for the states of, well, the physical states themselves. The associated Q-shape will be a superposition of the corresponding quasi-classical Q-shapes. So there we have the mapping between those two. Okay, and then you would define specific collapse operators to basically collapse these quasi-classical states into, to collapse the arbitrary states into, or in the superimposed states onto the quasi-classical ones that correspond to the actual physical reality. So that's the extension you need to make if you want to make IIT compatible with, the quantum observations that we see. That's at least one way of doing it, and that's the way they follow in this paper. The next thing that we need to sort of take into account in this case is something called continuous collapse dynamics. So we need, we relax the assumption of having absolute super resistance because we couldn't get that to work with the Zeno effect. So remember the oscilloscope that we tried to measure? If we had this sort of very strict super resistance, we would not be able to see a change in physical reality as, for example, the indicators of an oscilloscope. So we relax that assumption here. And what we need to do now instead is, because we have this weak form of super resistance, we need to have some sort of a dynamics for how we resist being in a superposed state. And that's what we describe with these continuous collapse dynamics. So these are collapse dynamics that are spread out through time and therefore continuous. Similar to the other things we discussed in this paper, there are a number of ways that you could model this or describe it. The paper uses a generalization of these two right here, because they're rather similar in the way they're set out. And what you do is basically you let the amplitudes of the Q-shapes determine how likely they are to collapse. So very similar to the standard notion of quantum mechanics, where you have basically the strengths of different states in combination with the Born rule to describe how things collapse into those states. Very similar to what we're doing here. So we're saying that the Q-shape amplitudes govern how likely something is to fall into or collapse into that particular state. So we're doing the exact same thing, and the system then will over time collapse into a specific Q-shape with probability given by its initial squared amplitude. So that's basically the rule that we get to after following this sort of this sort of framework. And very similar to standard quantum mechanics again, we rely on a modified version of the Schrödinger equation to describe the system. So we showed the Schrödinger equation in the previous video, so check that out if you haven't seen it. But the modification that we're doing in this video is basically to include these collapse dynamics. And you can see down here the updated Schrödinger equation, which is a bit more complex and a bit more, well, includes a bit more information. So we have a nonlinear stochastic collapse term here, and that's the one indicated in blue. And that's combined then with the standard linear deterministic evaluation or evolution of the Schrödinger equation. We also have a collapse rate, which is lambda here, and it's defined in such a way that it depends on the Earth mover distance between Q-shapes. So again, this is a concept from IIT. If you're not familiar with that, I would recommend checking IIT out. But EMD, or the Earth mover distance, basically tells us how similar to Q-shapes are. So the rate of collapse will then depend on the similarity of these two shapes. So that's how we would describe the continuous collapse dynamics. And we want to now sort of ground this in, we want to evaluate whether this model that we now constructed makes any sort of sense. If we can do reliable predictions with it, how well it describes, nature as we know it, how simple it is. That's another key criteria. So that's what we want to do next. And the best way to do that is to try and ground it in experimental tests. So to begin this section, we want to, just start by saying that it's in theory possible to measure if a system is in superposition of any supersystem property. It's, on the other hand, extremely difficult to do so. So the good thing about this is it gives us the framework to sometime in the future evaluate whether these hypotheses that we're making right now have some bearing and actually make some sense. But as of now, it's very difficult to do so. And the biggest experiment that's been done, so generally this becomes harder the more complex your systems become due to the way things need to be prepared in order for these experiments to make sense. And the biggest experiments that have been done up to date are of atoms that are around 2,000, or molecules that are of around 2,000 atoms in size. And that's, a lot smaller, of course, than, let's say, a human body or even something like, very primitive forms of being. So, as quantum mechanics evolve and also as simulations evolve, it might be, or as quantum computing evolves rather, it might be possible to actually simulate our brain or other primitive organisms in a more detailed way, and therefore find answers to these questions, whether they can bring about superposition or collapse it that way instead. So actually doing it in the physical setting might be very hard, but you might be able to construct a good enough simulation to actually get some information about what we're trying to solve here. So that's one potential way forward. And when we discuss this, it becomes quite relevant how fast the models collapse. So in the previous slide, you saw that we have a collapse rate here. And depending on how, on the size of that collapse rate, your systems would collapse faster or slower. It makes quite an important difference, if they collapse faster, if they collapse slow due to measurements. Because if you think about how we would measure this or verify a theory like this, we're not saying that our model is absolutely super resistant. So we would be able to see systems in a superposed state, but the thing is they would generally collapse quite soon. So just because we find something in a superposed state doesn't mean the theory is false. But if we find lots of them, then that would be an indication that, okay, things don't seem to work the way we thought they would. But because we do, in fact, allow states to be in a superimposed state, even with this model, it's not as simple as just finding something to prove the existence. And because of this, the collapse rate plays a role. So if you have a very fast collapse rate, you would never expect to see any of these superposed states, or at least they would be extremely rare. So potentially we would even be able to test that now or even in the very short future with quantum computers. The only thing you would really require is that you generate some sort of Q shape. So let's imagine in quantum computers right now, we would be able to generate a Q shape like this that's sufficiently complex to basically, yeah, give rise to a non-zero phi and then also a Q shape. If we assume that there is no threshold for phi, but it can go arbitrarily low, then this would be actually quite doable right now. And we could already test this. So if we constructed something like this and found that it wasn't a superimposed state, then it would be hard to justify that fast collapse models are actually true. So that's one thing we could do in the very short-term future. That's, that being said, it would be harder to validate or falsify a slow collapse model, because there you actually allow superpositions to be in place for a longer amount of time. And so that's a problem. Also, if we look at the quantum computing community right now, there seems to be a tendency for us to be able to observe larger and larger molecules in superimposed states or superposed states. And this is a problem for a model like we're describing, right? If we have a fast collapse model that depends on any non-zero phi, then we wouldn't expect them to be in superpositions, at least not for a significant amount of time. But that seems to contradict recent advances in quantum computing. And there are a few ways around this. So we could modify the model to accommodate for these findings. So for example, we could require a threshold for when we actually assign a non-zero phi to a system. So we wouldn't possibly allow it to go continuously down to zero. That would be one way around it. Another way around it would be to revert to a slow collapse version. So we would, throw away the notion that we have of a fast collapse model and revert to a slow one, allowing for more superpositions. So that would be one way. Or we could reject IIT for other models of consciousness. So IIT, as we said in the beginning, is not like a unique model of consciousness. There are many models of consciousness, and either of them could be correct. The thing that makes IIT very workable in these kinds of scenarios is that it gives us verifiable predictions, and that's a weakness of many other consciousness models. So that's why we're gravitating toward using that, but there's nothing cut in stone that this is the way reality is, right? It could be another consciousness model that does this better than IIT. And so, as a final way out, we could try and modify that model too. So those are some experimental findings. And last, we want to also talk about some of the philosophical criticisms that people have posted for this kind of framework. So the first thing that we might ask ourselves is, what is even a superposed state of consciousness? As we said in the beginning, we're kind of getting back to the problem that we were trying to solve in the beginning. We're allowing now superpositions of consciousness when we really wanted an understanding of how does the wave function collapse. So it seems like going in the wrong way, but then again, it might be that reality is in this way and that we're just not very used to thinking about things in this manner, with our monkey brains. So it could be an explanation, right? But Wagner, for example, who's one of the early pioneers in this field, said that it was absurd for a subject to be in a superimposed state of consciousness. And, from introspection, that feels correct. It feels like you shouldn't be in a state of superposition. You have one mental state at the same time, right? You don't experience some sort of overlap between different states of consciousness. But it's very hard to say something about whether or not this could in fact be the case. Like maybe you have states of consciousness that are in superpositions, but you're unable to feel them. Let's say you only feel the one that is the strongest. That would be one sort of explanation for it. It's unclear as well what it would even feel like. Like, it might be that we don't observe it at all. And the theoretical fruitfulness that we now see by accepting this point of view might be adequate to allow it for the current, let's say, state of affairs. We're doing the same thing in the physical version of quantum mechanics. We're allowing superpositions of states without exactly knowing why they would be in a state like that. And doing the same for a model of consciousness would not be absurd by any means. So another question we might ask is, macroscopic superpositions. So could it be that we have macroscopic objects that also are in superposition, and if they don't collapse until we measure them, they would basically be in a superimposed state all the time? I mean, as this model goes, we would, in theory, allow it. Like, we don't have anything against that according to the model framework that we developed. It might be, however, that they are correlated with humans, so that, even if they exist somewhere and are not conscious by themselves, they might actually collapse the wave function. I mean, another way of explaining it, or another way of looking at it, would be that IIT itself gives them some sort of consciousness, because like systems do not have to be organic for IIT to give them consciousness. Certain structures are conscious by definition according to IIT because they constrain integrated information, and extending what we accept as being conscious to well, to wider scope of objects like that, let's say a pen would be conscious, is something that feels kind of arbitrary and like a bad model, let's say. But we don't have any empirical evidence to really justify either or in that case. Like, who are we to say that the pen is not conscious by the, let's say, rigorous way of defining consciousness? So not in the way we necessarily think of it when we say consciousness, in the sort of arbitrary ways that we tend to say it, but really in a formal setting. It could be that the information constrained by that system allows it to be conscious. So, I mean, that's still something that would, in that case, collapse the wave function according to the framework that we now developed. And so in that case, macroscopic objects would not be in a superposition. But in principle, they could be according to this, and that is perhaps a weakness of the methodology. Another thing would be how consciousness appears in the universe. So what is basically the first occurrence? And this would be, well, a very hard thing for absolute consciousness models to justify, because we're basically saying, according to the Zeno effect, we would not allow for such instances to pop out of nothing. In the sort of less, or well, in the non-absolute or the approximate version of super resistance that we develop, that would be a possibility. So we're allowing for that within our framework. You could have something like a spontaneous eruption of consciousness that, you know, goes from a universe without it to a universe with it included. So it's not like a nail in the coffin for this kind of model, you know, to have to arise from nothing. With that being said, for the absolute versions, that seems to be another shortfall. So to wrap up basically what we have so far and to conclude this call, we started with an initial superselection collapse model that was very simple, but was suffering from the Zeno problem. So that is, things could not change their states. And that's, you know, really a crucial problem for that kind of methodology. So we moved away from that and basically expanded our model to something a bit more complex. And we were able to avoid the Zeno problem by requiring or allowing conscious superpositions and also continuous collapse dynamics. So those are the theoretical foundations that we talked about in the early parts of this video. And the only way around this, or like to break this, was between the strong link of definite states and consciousness, is to go away from the notion of having a mapping between eigenstates of PCC observables and then also states of consciousness. So PCC observables are the physical correlates of consciousness, and we didn't talk about the eigenstate breaking in detail. Perhaps that's something we'll talk about more in upcoming videos, but it gets rather technical, and we're already sort of well ahead of, or well over time for this video. So it's a field that they're not really investigating that much in this paper, but it's definitely something that they're advocating that further research should be conducted within. So that would also be an interesting avenue for further exploration. And as a final result, the simple model we then came up with was not as simple or powerful as some leading interpretations of quantum mechanics that we have right now. And yeah, that's in some ways a shortfall of the methodology, because really what we're trying to do is come up with something that explains reality and does it in a rather simple way. And the simple part of this doesn't really seem to be there for this model. With that being said, this is still a topic of research that deserves further attention, and there are plenty of avenues to expand this research that are not yet discovered or explored. So it's really quite early to say anything definitively of what we can do within the field, but at least this expands the notion that we have and gives us a model of what would it be like to model consciousness and see what effects it has on the physical reality as we know it. So that's where we're going to leave it for now. Thanks a lot for making it through both of these videos. I know they're quite lengthy and quite technical at times, but I enjoyed it. I hope you did too. See you in the next video, and take care.